Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about diffraction gratings. I actually have a little diffraction grating right here in my hand, and I also have a laser, just a single little green laser that I can shine basically into the camera or wherever. And if I have this little white board and I shine the laser on the board, you can see there's one spot that shows up on this board. But if I take the diffraction grating, I hold it so that the laser shines through the diffraction grating at the board, you can see that there are now more spots. You can see a few spots on this board. No diffraction grating, diffraction grating. You can see some more spots appearing to the sides of the main spot. So in today's video, what we want to do is discuss what this diffraction grating does, how it works, and so on. For what it's worth, one other example, I can tilt this up to look at the lights overhead, and if I stick the diffraction grating over them, you can see a set of rainbow colors from the light. If I remove it, you just get the light, put it here, you get that little rainbow pattern. And so we can discuss how all these things work in today's video. Now, to understand how a diffraction grating works, we have to kind of recall a few things from the previous videos that I've made. Really, you need to have watched the double slit and the interference from multi-slit videos. And what you'll recall is that the double slit gives us interference maxima and minima, and that multi-slits give us more interference maxima and minima, but of two sorts, if you will. The pattern that you end up getting from the multi-slit interference basically ends up looking like this. If this is the intensity and this is your position, basically you end up getting a maximum, and then you end up having some number of secondary maximum, and then a primary maximum again, and then some number of secondary maximum, and then the next primary, and so on. And the number of these secondaries, these secondary maximum, depends on the number of slits. So n slits implies n minus 2 secondaries, or secondary maxima, between each primary. It also implies that the intensity of the primary is going to tend to be n squared times the intensity of a single slit, which is also the intensity of these secondaries when there are secondaries. If you have only two slits, then there's no secondaries, but you could still define a slit intensity. Now, here's where I have to kind of break with my previous definition. This is where the other textbook writers who choose to use the distance being the distance between the two farthest are able to be more consistent. They paid for it by being less consistent with what they had written up to that point, but they get to be more consistent now in transitioning to the diffraction grating, whereas I have to kind of break with my notation here. A diffraction grating basically consists of a multitude of slits. As an example, this diffraction grating that I was using earlier for demonstration purposes has 500 lines per millimeter. What that means is that in each millimeter of distance along this slit, each millimeter this way, I have the equivalent of 500 slits. So if I have a laser beam that is 2 millimeters across, then it is passing through 1,000 total slits. Now obviously that means, from what we've said back here, that the primary peaks, these peaks right here, these would be my primary peak, these right here would be my secondary peaks or single slit peaks. My primary peak is then 1,000 times squared, or 1,000,000 times what we would expect for the secondary peak. For most intents and purposes, that is akin to saying that all the light is in my primary peaks and virtually none of it is in my secondary peaks. Now there's further effects that we can include. It is a diffraction grating. We would want to maybe also impose the envelope for single slit diffraction upon these patterns. It turns out that you have a true central primary, and then secondary peaks after that are weaker and weaker and weaker when you're going through at normal incidence. The major kind of parameter that we use is again D, but instead of using D, we might use something like lines per millimeter. And so in some sense this is 1 over D. So this is 1 over D, D in millimeters. Okay, so with that said, where do we expect the primary peaks, which are basically those individual dots that we saw in the little first demo? Where do we expect those to be? Well, this is being consistent with my notation again. We still expect for D times sine of theta to be equal to n times lambda. Same as with the double slit, same as with the multiple slits, and D even has the same definition that I've been consistent with using. Now where things get a little different here is that the slit width, in order for there to be this many slits, must be very small as well. So if I have 100 lines in a millimeter, then my slit width can be no greater than half of 1/100th of a millimeter. And again, on this one, I actually had 500 lines per millimeter. So I'm looking at roughly 1,000th of a millimeter as my slit width. And that basically means in turn that I'm looking at only about a factor of 2 or so bigger than my wavelength. If I'm using a green laser, the wavelength is typically 512 or 532 nanometers. Okay, so roughly a factor of 2 difference between slit width and basically like beam wavelength. If I go to red, then it's maybe a factor of 1.5 times the wavelength. And I can cram more lines per millimeter as well. But this equation still is the operating equation. Essentially, this means that we can predict where the bright spots are. All right, so as an example, the laser pointer that I was using had a 532 nanometer wavelength. And we illumined this 500 lines per millimeter diffraction grating, and then it traveled maybe 20 centimeters or so to get to the little screen that I was using. So we might ask, how far apart should the central and first order bright spots be? All right, well, basically what we would do to solve for that is we have to solve for theta and then use that theta to get a distance. So if I'm drawing this diagram, I have basically my diffraction grating, which is sometimes drawn like this to represent a grating. I've got a screen. This distance right here is 20 centimeters. And then essentially I expect the n equals 0 at theta equals 0. That's assuming normal incidence, of course, but if I put a 0 in for n on this equation, then I have d times sine of theta is 0. D is not 0, so I just have sine of theta is 0, and that's 0 degrees. And so then I also have maybe my n equals 1, and this is at theta 1, and I have a distance y between the two of them. And so looking at this triangle that I can draw here, I can see if this right here represents theta, or theta 1, and this represents y1, then the tangent of theta 1 is equal to y1 divided by L. And it's just using a right triangle geometry. And we also know from this equation that d times sine of theta 1 is 1 times lambda. So d times sine of theta 1 is equal to 1 times lambda. So this right here represents my lambda. This right here represents my L. And this right here is 1 over d, except for that this is in millimeters and this is in nanometers. So I would need to maybe convert this over to nanometers. So 5.32 times 10 to the minus 4 millimeters instead of leaving it nanometers. And now the millimeters can cancel with each other, because if I rearrange this equation, I get sine theta 1 is equal to lambda over d. And so that is 5.32 times 10 to the minus 4 millimeters. And then d is 500, so 5.00 times 10 to the 2 inverse millimeters, lines per millimeter. So if I multiply those two together, then I've got my theta. And now I take the arc sine of that to get theta 1. So this is basically saying sine theta 1 is 0.266, and therefore theta 1 is equal to like 15.4 degrees. All right, so now I can plug into this equation. This one now says y1 is L times tangent theta 1, and so y1 is 20 centimeters times the tangent of 15.4 degrees. And so y1, if I take the tangent of that, is 0.275, and that times 20 centimeters gives me about 5.52 centimeters. This is about 5.52 centimeters. And that's, for 0, it's at 0. So this is actually the distance between the central peak and the next one over. About 5.5, so about 2 inches. And you could go back and look on the demo earlier. It does get altered slightly if I go through at an angle. It's awfully hard to hold stuff steady at normal incidence, but this is not an unreasonable estimate for how far apart 2 consecutive bright spots were. All right, the other part of what I may, or what I should discuss here is the other part of the demo, which was that when I held the diffraction grating up to the camera and looked through it at the light, you saw that little rainbow on the sides of the light. You could still see the white light in the middle, but then you also saw that rainbow on either side of it. So why does that happen? Well, again, going back to this equation, d sine theta is in lambda. So d sine theta is in lambda. This is kind of the rainbow, diffraction rainbow. This is coming to us because we have different values of lambda for different colors of light. So let's say that we take n equals 1. So what if n equals 1? Then you basically have d times sine theta 1 is equal to lambda. Okay? Or in other words, sine of theta 1 is lambda over d. Now we're looking at white light. So white light, such as from the fluorescing light bulbs in my office, the sun, an incandescent bulb, anything that has a spectrum to it. Many different colors together. Each color is its own wavelength. So that means that I have a bunch of different wavelengths here. D is fixed. It's how many lines per millimeter I have here, or 1 over that number. Therefore, I should get a bunch of different thetas. So this implies different theta for each lambda. Different theta for each lambda. So in other words, colors spread out. So colors spread after passing through the grating, of course. Now in the center, where theta equals 0, what happens? Well, if theta equals 0, n can also equal 0. And so all of the wavelengths have the same location for n equals 0. They're distributed a little bit because I have an extended source with these fluorescent lights. If I had a line source, like if I could take that fluorescing light and put a little slit so that the light just barely comes out of it, and then image that slit so that it looks like a line at the location of the grating, then I would have kind of like a very sharp set of individual colors to look at. And this is the basis of using diffraction gratings for spectrometers, grating spectrometers. Basically what you do is you shine your light source, maybe it's a star, maybe it is a sample of some sort, and you illuminate it so that it fluoresces, or if it's a star you just kind of look at it. And then you send that through a diffraction grating, or a prism will also work, but we'll use diffraction grating here. And you look and see where do lines show up on a detector array. And where those lines show up, that tells us what the wavelength is. And so if we know what the wavelength is, then we basically know what kind of atom is it that those wavelengths could correspond to. Each atom has its own sort of like fingerprint by what wavelengths it tends to emit or absorb. Okay. One last little note. I've focused mostly on the transmission grating. There's such a thing also as a reflection grating. Transmission grating basically means you've got your grating like this, and you are going to send the light through it. So light comes in from this side, and then it splits off on this side. Reflection grating works very similarly. The math is pretty similar anyway. But instead of transmitting through the grating, your light is usually incident upon the grating like so. And then it reflects off the grating like so. And with the reflection grating, typically what we end up doing is going to non-normal incidence, and it gets a little bit more complicated there. I don't want to go into all of the details of like litro reflection and so on. But you can send in at a slight angle, and then your first order minimum, or excuse me, first order maximum is basically going to be light that's obeying the law of reflection as such. And so you'll get an apparent reflected light that is acting as if it was just reflecting off of this flat surface. And that's your n equals 0. And then your other orders are spread out about it. And you usually do it that way if you want to build like a pulse compressor for a high power laser system. Typically uses diffraction gratings at reflection rather than transmission, because they're less likely to be damaged and less likely to distort the beam in basically passing through. There's other types of things that are called gratings, like there's the fiber Bragg grating, and that is more complicated still. Fiber Bragg grating is used a lot in essentially you send a signal and it reflects back light that is based on a periodic modulation of your refractive index in your fiber. And so the wavelength that gets reflected back tells you this is what the spacing is of that periodic grating, essentially. And you can use it to do things like measure stress or strain. So you can attach it to, let's say, to like a metal support strut on a bridge or something, and you want to measure stress and strain. And so when that strut either compresses or stretches, the fiber will compress or stretch as well, and that will change the wavelength that gets reflected back to you. And so you can detect, okay, how much was this compressed by? All right, well, that's all for today's video. Hopefully you've learned a bit from watching it. Hopefully you enjoyed it, and hopefully you saw the demo and enjoyed that as well. I don't do as many of those on these videos because I don't have a great setup for doing that right now, but I do hope that you got something out of that too. As always, thanks for watching, and see you in the next one.